Picture this. After months of hard work, you've finally perfected your design in CAD. Every line, every curve, every tiny detail is flawless. You've checked the measurements a dozen times and everything fits together perfectly on your screen. It feels like you've created a masterpiece, and you can already imagine the finished product in your hands. Confident in your work, you send the files off for injection molding. You hit send on the order, certain that you've nailed every aspect of the design. Now all that's left is to wait for your vision to become reality. The day arrives, you unbox the freshly molded parts, eager to see your design come to life. But as you measure one, your heart sinks. It's too small. The dimensions are off, and suddenly, your excitement turns to confusion. Snap fits that should click together are loose. Lids that should seal tightly now wobble. Gears that were meant to mesh perfectly grind and skip. Everything feels just a little bit wrong. You rush back to your CAD file, double-checking every measurement. The numbers are still perfect, exactly as you designed them. You even review the manufacturer's process. The machines are running smoothly, and the technicians assure you everything went according to plan. So, what went wrong? Welcome to the world of plastic shrinkage, a hidden challenge that every designer faces. Shrinkage is the invisible force that transforms digital perfection into undersized reality. It's the reason your flawless CAD model doesn't always match the part you hold in your hand. This isn't a manufacturing error, it's not a mistake by the factory. Shrinkage is a fundamental property of plastics, a natural part of the molding process. If you don't account for it in your design, your masterpiece can quickly become a pile of scrap, costing time and money. But here's the good news. Shrinkage isn't unbeatable. Once you understand how it works, you can design around it and avoid costly mistakes. It's not just about making everything a little bigger. It's about mastering the physics, knowing how different plastics behave and adjusting your design with precision. By the end of this journey, you'll see shrinkage not as a curse, but as a challenge you can conquer. With the right knowledge, you'll turn your digital dreams into perfect, real-world parts. So, what is shrinkage? Simply put, it's the reduction in size as plastic cools from molten to solid. Imagine a cake that settles as it cools. Plastics do the same, but the stakes are higher. When injected, plastic molecules are energetic and spaced out. As they cool, they slow down and pack closer together, shrinking the part. There's also a second effect. Polymer chains organize themselves, sometimes crystallizing and squeezing out even more volume. So, shrinkage is a 1-2 punch: thermal contraction and molecular packing. It's not a defect, it's a predictable property of polymers. The trick is to anticipate it and design accordingly. If you do, shrinkage becomes a controlled outcome, not a surprise. That's how you turn a potential disaster into a design advantage. Not all plastics shrink the same way. There are two main families, amorphous and semi-crystalline. Amorphous plastics like ABS and polycarbonate have tangled, random chains, so they shrink less and more predictably. Semi-crystalline plastics like polypropylene and nylon form tightly packed crystals as they cool, causing much higher shrinkage. The more crystalline the structure, the more the part shrinks. Cooling rate matters too. Fast cooling means less crystallinity and less shrinkage. Slow cooling means more. Predicting shrinkage in semi-crystalline plastics is trickier, but gives you more control levers. Knowing your materials family is step one in designing for shrinkage. Choose wisely, and you'll avoid nasty surprises. Shrinkage alone isn't the real problem. Warpage is. Warpage happens when different parts of your design shrink at different rates. Uniform shrinkage is easy to handle. Just scale up the mold. But if one section cools slower or shrinks more, the part bends, twists, or curls. Thick ribs, uneven walls, or inconsistent cooling all cause non-uniform shrinkage. The result? Parts that don't fit, lids that don't seal, and surfaces that warp. Good design minimizes these risks by promoting uniform wall thickness and even cooling. You can't stop shrinkage, but you can control how it happens. The goal? Shrink uniformly, keep your shape. That's how you avoid the dreaded banana-shaped part. Warpage is the true enemy, designed to defeat it. Master this, and your parts will fit and function as intended. So, how do you control shrinkage and warpage? These are two of the most common challenges in plastic part manufacturing. And while some factors are out of your hands, there are several you can directly influence to achieve better results. Here are the key levers you can pull to take control of your process and outcomes. First, material choice sets your baseline shrinkage. Amorphous plastics like ABS or polycarbonate generally have lower and more predictable shrinkage. Semi-crystalline plastics, such as nylon or polypropylene, tend to shrink more and can be trickier to manage. Selecting the right resin is your foundation for success. Wall thickness is critical. Uniform walls cool and shrink evenly, minimizing internal stresses. Thick spots or sudden changes in thickness can lead to uneven cooling, causing warpage, sink marks, or even cracks. Always aim for consistent wall sections throughout your design. To add strength, use ribs instead of simply making walls thicker. Well-designed ribs reinforce your part without creating thick junctions that can trap heat and cause defects. Pay attention to rib placement and thickness for optimal results. Gate location is another crucial factor. It determines how molten plastic flows into the mold and how the part cools. Poor gate placement can lead to uneven shrinkage, so plan your gate locations carefully to ensure balanced filling and cooling. Mold temperature also plays a big role. Warmer molds allow the plastic to cool more slowly, which can increase shrinkage but reduce internal stresses and improve surface finish. Cooler molds speed up production but may lock in stresses or cause incomplete filling. Packing pressure is your tool for squeezing extra material into the mold as the part cools. Higher packing pressure can reduce shrinkage and help fill out fine details, but too much can cause flash or stress. Fiber reinforcement, like adding glass or carbon fibers, can dramatically reduce shrinkage in the direction of the fibers. However, if not managed properly, it can introduce warpage in other directions, so fiber orientation must be considered in your design. Think of each of these factors as a dial you can turn to steer your design towards success. Adjusting them thoughtfully lets you fine-tune your process and avoid surprises. The key is to consider these factors early in the design phase, not as an afterthought. Early planning helps you avoid costly mistakes and last-minute redesigns. The best designers use these controls proactively, making shrinkage and warpage work for them, not against them. They collaborate with manufacturing teams and use simulation tools to predict outcomes. Don't leave your results to chance. Design with intention, test your assumptions, and refine your approach as needed. That's how you get perfect parts every time, by understanding and controlling the factors that matter most. Let's walk through compensating for shrinkage, step by step. This process is crucial for ensuring that your final product meets the exact specifications and quality standards you aim for. First, pick your material and get the exact shrinkage rate from the datasheet. This information is vital as it forms the foundation of your calculations. For example, polyoxymethylene, POM, might have a 2% shrinkage rate. Knowing this helps you anticipate how much the material will contract as it cools. Next, calculate the mold size. Mold dimension, =part dimension, 1, shrinkage rate. This formula is your key to adjusting the mold dimensions accurately. For a 50 mm gear, that's 50 zeros. 98 =51.02 mm. This precise calculation ensures that the gear will fit perfectly once it cools and shrinks. Apply this scaling to every feature: outer diameter, bore, teeth, everything. Each aspect of the design must be adjusted to maintain the integrity of the final product. Most CAD software can scale the whole model for you, making the process more efficient and less prone to human error. For fiber-filled plastics, check for different shrinkage rates in different directions. These materials can behave unpredictably, so extra care is needed. You may need to apply different scaling factors along different axes. This often requires simulation. Simulations can provide insights into how the material will behave under various conditions. Don't guess. Use real data and communicate with your mold maker. Collaboration ensures that everyone is on the same page and working towards the same goal. Compensate up front and your parts will come out right the first time. This proactive approach saves time and resources in the long run. This is how you turn shrinkage from a problem into a solved equation. By addressing potential issues early, you ensure a smoother production process. Precision here saves you time, money, and headaches. Every detail counts when it comes to achieving the perfect fit and function. That's the magic of proactive design. By anticipating challenges and addressing them head-on, you create products that meet and exceed expectations. Even pros make shrinkage mistakes. Here's how to avoid the big ones. First, don't ignore anisotropic shrinkage in fiber-reinforced plastics. Always use both flow and cross-flow values. Second, never use a generic datasheet. Get the exact shrinkage rate for your specific material and grade. Third, avoid double compensating. If you scale your CAD, Make sure the mold maker doesn't do it again. Communicate clearly about who applies the compensation. Finally, don't design features that can't be molded, like wildly varying wall thickness or sharp internal corners. No amount of compensation fixes a bad design. Think manufacturability from the start. Avoid these pitfalls and you'll save time, money, and frustration. Shrinkage is predictable. Mistakes are not. Be smart, and your parts will be too. In the end, manufacturability is everything. Mastering shrinkage is the bridge between digital design and real-world success. Ignore it, and even the best ideas fail. Understand it, and you control the outcome. Uniform wall thickness, smart gate placement, and the right material choices are your tools. Use them, and you'll avoid costly revisions and delays. Designing for shrinkage isn't just about size, it's about mindset. Embrace the constraints, and you'll create products that work in reality, not just on screen. Fewer mistakes, faster launches, better products. That's how you win at design and in the marketplace.